Our solution, Trinetra Grid, is designed as a convoy routing and monitoring engine that is explicitly aware of the mission context and the dynamic state of the environment. At high level, Trinetra Grid is organized into 4 layers that work together in a coherent architecture. First, we have the input and data layer. Here, the planner specifies the mission details, the start node, the end node, the mission mode, such as peace, operation, or disaster, and relevant convoy information like size and priority. This layer also provides the base road network represented as nodes and edges, and any historical or incident data that can inform routing. Second, we have the routing and grid engine. This component takes the road network and the mission parameters, assigns scores to each road segment using multiple factors, constructs a focused corridor between start and end, and overlays a grid on that corridor. This grid layer allows to localize anomalies in a very compact way. Third, we have the execution and rerouting layer. This is what runs on the convoy device. Instead of doing heavy computation in that field, it carries a carefully chosen subset of the map and pre-computed routes, and it knows how to switch routes quickly when it receives small anomaly updates. Finally, we have the security and audit layer, which we call Raksha ledger. This is a hash chain ledger that records each critical event, such as route planning, anomaly detection, and route changes, in a way that makes later tampering easy to detect. Let me briefly describe how a mission starts in the system. At headquarters, the planner selects a start node S and end node E and a mission mode. Each mode corresponds to a different balance of priorities. For example, in peace mode, we may weigh civilian impact more heavily. In operation mode, we may emphasize risk and terrain. And in disaster mode, we may accept more difficult terrain to save time. To keep the problem trackable and focused, Trinetra Grid does not attempt to optimize over an entire country. Instead, it constructs a mission corridor. It first computes a baseline shortest path between S and E, then it takes all nodes and edges within a chosen distance, for example, 5 to 10 kilometers around the baseline, and defines that region as a corridor. All subsequent computation, multi-factor scoring, grid overlay, anomaly handling, and rerouting takes place within this corridor, which is large enough to contain meaningful alternatives, but small enough for efficient real-time use.
Within this mission corridor, Trinetra Grid represents the road network as a directed graph. Each node represents a significant point, such as intersections, bridges, checkpoints, fuel, and medical facilities, or known-risk hotspots. Each edge is a directed road segment from one node to another, and it carries both geometric information and a set of normalized factor scores. For each edge, we store factors such as a normalized travel score, a risk score, a terrain difficulty score, a civilian impact score, and a weather-related score. All of these are scaled between 0 and 1, where lower values represent more favorable conditions. For each mission mode, peace, operation, or disaster, we define a set of weights over these factors. For example, in operational mode, the weight on risk and terrain may be higher, while in disaster mode, the weight on time may be dominant. Trinetra Grid then uses a multi-factor cost function for each edge. In other words, we do not simply take the shortest or fastest route, we use an algorithm that combines these factors with mission-specific weights to compute the most appropriate route for that mission. Using this cost function as the edge weight, we run a standard pathfinding algorithm such as A star star over the corridor graph. The result of this optimization is the primary route from S to E that best reflects the priorities of the chosen mission mode. However, we assume that conditions can change, so Trinetra Grid also pre-computes backup routes. For each key node along the primary route, ideally, every node, or at least at regular intervals, we invoke the same multi-factor algorithm to compute 1 or 2 alternative routes from that node to the destination. We generate these alternatives by adjusting factor weights or by applying penalties to certain high-risk or congested areas so that the alternatives are genuinely distinct and meaningful. For each route, primary and backup, we also compute which grid cell it traverses using the grid that will be described shortly. This gives us a mapping from the given route to a set of cell IDs. Before the convoy departs, the device is loaded with the primary mission optimized route, a set of backup routes for the key nodes along the way, and the mapping between each route and the grid cell it uses. This ensures that the device has multiple pre-evaluated options and does not have to perform heavy optimization in the field.
I will now describe how Trinetra Grid uses a grid overlay and an event ledger to handle anomalies in a precise and accountable way. Once the corridor has been defined, we overlay it with a regular grid. For example, cells approximately 1 kilometer by 1 kilometer. Each cell is given a unique identifier, such as C7, and a status that can be normal, warning, or critical. For each road segment in the corridor, that is, for each edge in our graph, we calculate its geographic midpoint and determine which grid cell contains that point. We then record a mapping from the edge to corresponding cell. This allows us later on to answer the question which road segments are inside the particular cell very efficiently. And where this is used? When an anomaly occurs, it can be reported in several ways: manually by an operator at headquarters, automatically by a sensor or checkpoint, or via an external field such as weather or incident API. In all cases, the anomaly includes at least a location and a type, for example, bridge collapse, accident, security threat, or flooding, along with a severity level. Trinetra grid first maps the anomaly's latitude and longitude to a grid cell. Supposing it falls into cell C7, the system then updates the status of C7 to critical, warning, depending on the severity. Using the pre-computed edge-to-cell mapping, we can immediately list all the affected edges, that is, all road segments whose midpoints lie within the cell C7. These edges are now considered unsafe or heavily penalized. For each convoy, we examine its current planned route as a sequence of nodes, convert that into its sequence of edges, and check if any upcoming edges appears in the affected list. The first such edge marks the point at which the route becomes unsafe. The node immediately before the edge is chosen as the change point node, the last safe node from which we should diverge to an alternative route. In parallel, every important step in this process is recorded in our Raksha ledger. What is Raksha ledger? Raksha ledger is a hash changed event log. Each event, for example, plan created, backup routes pre-computed, anomaly detected, route changed, or device hack, is stored with a timestamp, a structured payload, the hash of the previous event, and a new SH256 hash computed over all these fields. Because each event includes the hash of its predecessor, the entire ledger forms a cryptographic chain. If someone later attempts to modify or delete an event in the middle, the chain of the hashes will no longer be consistent. This makes the ledger tamper-evident. Practically, this means that for any machine we reconstruct, a clear, trustworthy narrative. What the original plan was, which anomaly was detected in which grid cell, which change point node was used, which alternative route was selected, and when the convoy device acknowledged the change. In summary, the grid overlay allows us to localize anomalies in space. The anomaly logic identifies the appropriate change point along the route, and the Raksha ledger ensures the entire decision process is transparent and verifiable.
Let me now describe what happens on the convoy side. The computation and connectivity are constrained. The convoy device does not carry the full global map and it does not perform large-scale optimization in real time. Instead, before departure, it is provisioned with the primary mission optimized route, a set of backup routes from important nodes along that route, and for each route, the list of grid cells it traverses. When an incident is detected, headquarters does not send a heavy map update. Instead, Trinetra grid sends a compact anomaly packet. This packet is a small JSON structure containing an anomaly identifier, the type of anomaly, a list of affected cell IDs such as C7, the security, a validity period, and a cryptographic signature of HMAC. Because this packet is only a few dozen bytes, it can be transmitted even over weak or intermittent networks. Upon receiving an anomaly packet, the device performs a clear sequence of steps. First, it updates the status of the reference grid cells in its local copy, making them as critical or warning. Second, it checks whether the currently active routes uses any of these cells by comparing the route cells list with the affected cell IDs. If the active route is not affected, the convoy can safely continue. If the route is affected, the device identifies the nearest change point node before the first unsafe segment. From that change point node, the device then reviews the preloaded backup routes. For each backup, it checks whether the route's cell set intersects with any critical cells. Routes that cross critical cells are eliminated. Among the remaining safe backups, the device selects the most suitable one based on the same multi-factor, mission-weighted cost function that was used at headquarters. Once a new route is selected, the device switches the active route to this backup starting from the change point node. The convoy now continues on a pre-validated, mission-consistent alternative path without needing to download an entire new map. At the next opportunity, the device also sends back an acknowledgement event, which is recorded into a Raksha ledger at headquarters. This closes the loop. The plan, the anomaly, the reroute decision, and the final acknowledgement that all capture in a tamper-evident history. To illustrate this with a short scenario, imagine a convoy traveling from base Alpha to forward Bravo. The original route includes a bridge between nodes N5 and N6. If that bridge fails, an operator makes the incident on the map. Tenet grid maps the location to cell C7, identifies the edge between N5 and N6 as affected, and selects N5 as a change point node. It sends an anomaly packet referencing cell C7. The convoy device receives it, recognizes that the current route uses C7, and immediately switches to a pre-computed backup route from N5 that avoids all critical cells. Every step of this process is recorded in a ledger. In conclusion, Trinetra grid combines mission-aware, multi-factor route optimization, a grid-based anomaly detection and localization mechanism, pre-computed backup route anchored at key nodes, and a cryptographic link Raksha ledger for auditability. Together, these components transform convoy routing from a manual, reactive process into a systematic, adaptive, and accountable operation that continues to function even under weak connectivity and rapidly changed ground conditions. Thank you.